Hey everyone, this is our first day as we begin our discussion of the class of molecules known as lipids. I'll share with you all, this is one of my favorite topics to talk about, and so let's go ahead and get cracking. So lipids are substances of biological origin that are soluble in organic solvents, which is kind of atypical because most everything that we've talked about this semester, we've talked about solubility in aqueous solutions. In fact, it's kind of been implied that everything that we've done has been in an aqueous environment, and everything that we've talked about, save a few functional groups, have been kind of exclusively, or maybe most soluble in a non-polar, a polar solvent as opposed to a non-polar solvent. So lipids perform a couple of biological functions. Number one, lipids form a bilayer and are essential components of biological membranes. Number two, lipids containing hydrocarbon side chains serve as energy stores. And number three, many intra and intercellular signaling events involve lipid molecules. Now, there's a total of 5 major classes of lipids that we're going to talk about, and my plan is to introduce the first 3, fatty acids, triacylglycerols, and glycerophospholipids in today's lecture. We will get through some of the other ones, sphingolipids and steroids, in subsequent lectures. So let's go ahead and get started. Here are our fatty acids. Now, one of the things that I want you to recognize about a fatty acid is where each component, and when you hear that term fatty acid, well, the acid part is this functional group right here, our carboxylic acid. And as you can see, all of these carboxylic acids are shown protonated. Now, in terms of, a physiological environment, chances are that it would actually not be protonated like this, but rather it's going to be deprotonated. Now, what we've got here are a total of 4 different acids. There's steric, oleic, and linoleic, and alpha-linolenic acid. Now, when you look at these different acids, it's important to recognize kind of what distinguishes them from one another. So, like I said, the carboxylic acids have a long hydrocarbon side chain. Predominant fatty acid residues in plants and animals are between 16 and 18 carbons long. Now, the first distinction between our fatty acids are identifying and comparing and contrasting saturated versus unsaturated fatty acids. The nomenclature that we use to identify a saturated versus an unsaturated fatty acid is represented here. I'm going to pause. So this notation of C18:0, just a second. Nope, that's not what I want. I want this. There we go. C18 versus 18:2. Now the C18 indicates that the molecule we're talking about has a total of 18 carbons. Now, one thing that's important to remember about that, and important to just a little detail to include, is that our carboxylic acid carbon is included in that number total. So if we look at this fatty acid right here, steric acid. Steric acid is the common name for that fatty acid. It has 1 all the way up to 18 carbons. So it's an 18 carbon long fatty acid. So the question is it noted as C18:0 or 18:2? And the answer is, well, it's going to be denoted as 18:0. The reason for that is if we look at this fatty acid from carbon number 1 all the way down to carbon number 18, there are no double bonds. It is nothing but single bonds. This is what is known as a saturated fatty acid. Now, if we compare that to oleic acid here. Now again, carbon number 1, carbon number 18, so this would be C18, but then the question is, well, what number, if any, follows that colon? And the answer is it's going to be 1. The reason for that is because it has a double bond between carbons number 9 and carbon number 10. So this would be oleic acid is 18:1. Linoleic acid, by comparison, has one double bond and a second double bond. It has 18 carbons. So this is C18 colon 2. Linolenic acid, C18 colon 3. Okay, so that's our primary notation for fatty acids. Now, all double bonds have the cis configuration. The first double bond generally occurs between carbons number 9 and 10. When we look at oleic, linoleic, and alpha-linolenic acid, we do see that trend once again. These linoleic and alpha-linolenic acid are examples of polyunsaturated fatty acids, meaning they have 2 or more double bonds. The double bonds are not conjugated, meaning whenever you see a polyunsaturated fatty acid, you should expect to see a pattern of a double bond followed by a single bond, followed by another single bond, and then a double bond. So I always think about it as D, S, S, D, S, S, D, S, S, D. So this would be the pattern for a polyunsaturated fatty acid with 4 double bonds. Here is our alpha-linolenic acid. We've got double, single, single, double, single, single, double, and that's it. This is a polyunsaturated fatty acid with 3 double bonds. Now, it's an expectation that if I prompt it on either your 4th exam or on your final exam, like, hey, draw this fatty acid, be able to do that. And so basically be able to convert this notation to a structure. Now, another type of fatty acid that you may be familiar with are your omega fatty acids. Now, your omega fatty acids are really not that much different than the fatty acids that we've previously talked about, but they give a little bit more information. You've probably heard of omega-3, so omega symbol 3, or this omega, that kind of W minus 3. Omega-3 fatty acids are a little bit different. Now, one thing that I want to draw your attention to is here we just have an omega-3 fatty acid. We're not indicating how long this fatty acid is, so we don't know that it's 18 colon 1 or anything like that, or 18 colon 2. All that we know is there is at least 1 double bond, but where is that double bond? Well, that double bond is 3 away from the omega end. So if we think about carbon number 1, our carboxylic acid, and then our next carbon, our first carbon away from that carboxylic acid as our alpha carbon, well, then the methyl end would be our omega end. So this is a little bit of a counterintuitive way of thinking about nomenclature, because what we were looking at was labeling our fatty acids and their positions based on our organic numbering and nomenclature scheme, but this uses the opposite. Okay, these are also known as N fatty acids, so you should expect to see either omega minus 3 or N minus 3 to indicate an omega-3 fatty acid. And we'll get into some examples and how to draw them in a little bit. 16 colon 1 N minus 3. That means that we are going to start at our 16th carbon, and we're going to say 16, 15, that's 1, 14, that's 2, and then carbon number 13, that's where our double bond will start. Our double bond will be found between carbons number 13 and number 12. Now, they can get fairly complicated. C20 colon 5. Well, we're using the exact same scheme that we previously talked about. C20 indicates that we've got 20 carbons. Colon 5 indicates that we have a total of 5 double bonds. Now, those 5 double bonds, where are they going to start? They're going to start 3 away from our methyl end. So we're going to say 20, 19, 18. So that would be 1, 2, 3. 17 to 16, there would be a double bond. But then we still have that D, S, S, D pattern. So 16 to 15 would be a single bond. 15 to 14 would be a single bond. 14 to 13, that's our next double bond. And we're going to have a total of 5 of those in there. So let me go ahead and erase this all here. Okay, there we go. So be able to draw an omega fatty acid. Now C20:5 is a little bit complicated. I would, be able to draw something like C20:2 omega minus 3 and be able to do something like that. Now fatty acids, when it comes to the structures in classifying saturated and unsaturated fatty acids, you can kind of take some directions and maybe some advice, some thoughts, some commentary from nutritional commentary. Generally, if somebody's told to eat fats, or if they want to include, obviously they want to include fats in their diets, typically people are told that they should include polyunsaturated fatty acids as opposed to saturated fatty acids. And the reason for that is they're metabolized a little bit differently, but from a molecular standpoint, I think that it's always valuable to think about that. Saturated fatty acids, they're going to pack really tightly together. And so here what we've got is a model of a single saturated fatty acid and a single unsaturated fatty acid. Unsaturated tails are going to bend, so they're not going to pack quite as well with one another. I always kind of imagine that it's like, let's take I've got 4 pens. If I take these and imagine that all of these pens are saturated fatty acids, they're going to pack super tightly together. So in this space, so this range from here, from my thumb to my index finger, I've got four fats, 4 fatty acids. Now, if one of them is a saturated fatty acid, I'm going to replace one of my pens with something a little bit more flexible, this stylus holder. Here's my mono unsaturated fatty acid. Okay, I'm going to try to get this fat to pack right next to it. Well, it's not going to fit perfectly. So then it brings me another one. Well, that's not going to fit perfectly. So again, that space where between my thumb and my index finger, I'm not going to be able to pack 4 fats in there. Instead, I'm going to be able to pack, 2 or 3 or something like that. And I like to think about that and look at this figure right here. We've got a mixture of saturated fatty acids shown here with C. These are packed super well together. Whereas in D, we've got, let's see, I always like to think about this range from here, and I'll give myself, let's see, I don't have a quick way of measuring something on my screen, but if I were to take this same range and apply it here, I've got 5 fatty acids versus only 3 fatty acids right here. So when you're consuming lots of saturated fatty acids from sources like bacon or something like that, when you eat 1 square or 1 cubic inch of beef tallow or bacon fat or something like that, you're getting lots of fat there. You're getting lots of carbons that need to be broken down into CO2. So you're getting tons of energy from that. Whereas when you're eating polyunsaturated fatty acids with some saturated fatty acids in there, the amount of fat that you're getting is not nearly as much. So, you're not getting as many excess calories. Of course, if you're someone who is highly active, if you run 15 miles every day or something like that, well then you probably do need to have more saturated fatty acids because you need that energy. You need to be able to replenish that energy. So here what we have is a list of fatty acids. At the top, we've got our fatty acids that range from 12 carbons to 24 carbons. Then we have some polyunsaturated fatty acids and some monounsaturated fatty acids. Now, what I think is most important to recognize about this is look at our 12 carbons and our melting point, then our 24 carbons and our melting point. Now, our melting point for our 12 carbon molecule, our melting point is 44.2 degrees Celsius. I think that it's helpful to always say, okay, if you had a sample of N-dodecanoic acid, well, that is going to be a solid at room temperature. If you had N-tetracosanoic acid, well, that's going to be a solid at room temperature. Then what I'd like you to do is look at, okay, 16 carbons, 63 degrees Celsius. Yes, definitely a solid. All of these saturated fatty acids are a solid at room temperature. Now, I'm going to show a comparison between just our 16 carbon long fatty acid, N-hexadecanoic acid, and a monounsaturated 16 carbon long fatty acid. That is 16:1 delta 9. And I haven't talked about the delta numbering scheme, but this is basically a 16 carbon long fatty acid. The first double bond is found at carbon number 9. There's only one double bond, but what this has as a melting point is between 1 and 0.5 degrees Celsius. So this is a liquid at room temperature. Now, next up, when we have 18 carbons, okay, what happens to our melting point? 18 carbons, one double bond. The difference between these two fatty acids, palmitoleic acid and oleic acid, is 1 carbon. Or actually, I'm sorry, 2 carbons. 18 carbon, colon 1 versus 16 carbon, colon 1. That 16 carbon long molecule is a liquid at room temperature with a melting point at about 1 degree Celsius. Okay, then our 18:1 oleic acid, that is also a liquid at room temperature. Now that liquid at room temperature, well, the melting point goes up. So as our number of carbons goes up, so too does our melting point. Okay, so number of carbons and melting point go up together. Now then let's look at 18:2. So we've added one more double bond in there. We've gone from oleic acid to linoleic acid. We go from 13.4 degrees Celsius as our melting point to between 1 and 5 degrees Celsius. So these are all liquids at room temperature. In fact, you could look at this and say, well, all of our 16 carbon and longer fatty acids at room temperature, they are going to be liquids when they are when they are unsaturated. But what I want you to notice is that as our number of carbons goes up, so too does our melting point. As our number of double bonds goes up, that goes up, our melting point goes down. So that's a little bit of an unexpected turn of events, but that's worth noting. Now, in addition to that, it's important to remember that our number of double bonds is going to take precedent. So imagine if you have something, if you're comparing fatty acids that are getting progressively longer, okay, your melting point is going to continue to go up. But then if you're introducing more and more double bonds, so, you know, if you imagine a 24 carbon long fatty acid, let's say 22:1 and 24:2. So this is 22 carbons, 1 double bond. This is 24 carbons with 2 double bonds. I would anticipate that the melting point of this is maybe going to be lower than the melting point of this due to the fact that it has 2 double bonds. Then if you say 24:3, what's going to happen to our melting point? Well, that's going to continue to go down because as you introduce more and more double bonds, our melting point will diminish. Now here's basically that list again, but represented in a slightly different way. We've got our saturated fatty acids, our unsaturated fatty acids, the common names of those fatty acids, and the melting points of those fatty acids. It's not my expectation that you know the common names of fatty acids. There's a couple that I think are helpful for y'all to remember in your journey through biochemistry, one of them being palmitic acid, that's 16 carbons long, stearic acid at 18 carbons long, just because your most common biologically relevant fatty acids are 16 and 18 carbons long. Another one that I think is worthwhile is arachidonic acid. It's 20 carbons long, because that arachidonic acid is a fatty acid that gets broken down to form prostaglandins and molecules that induce inflammation, which we'll come up to that a little bit later. Okay, so we've talked about varying lengths of fatty acids. We've talked about the difference between a saturated fatty acid and unsaturated fatty acid. Here's those 4 fatty acids that we've previously talked about: stearic, oleic, linoleic, and alpha-linolenic acid. Now, again, I'm not expecting you to know these names, but I think that it might be helpful to, it's not going to get you any direct points on an exam or a quiz or anything like that, but I think that it is helpful to look at these and think about it as, okay, I have these fatty acids that I can kind of fall back on. I've got this information in my back pocket. So we have 4 fatty acids that what they share in common is they are all 18 carbons long. What makes them different from one another is 1 to 2 to 3 double bonds. Now, what we have touched on a little bit, but we're going to get into a little bit more, is the naming. C18:0, 18:1, N-9, delta 9. What's the difference between all of these? Now, that N scheme is the omega scheme. So N-9 is the same as omega -9. Now, what I think is helpful whenever you think about these fatty acids is, here what we have is omega -9, N-6, or sorry, N-9, omega -9, N-6 or omega -6, and N-3 or omega -3. Now, I'm going to start out with a commentary on the delta numbering scheme. The delta numbering scheme, if you look at those, delta 9, delta 9, 12, and delta 9, 12, and 15. What this is telling us is exactly where those carbons or those double bonds begin. Now, the delta numbering scheme, delta starts from COOH. So it starts right here. 1, 2, 1, 1. Okay, now I'm going to go ahead and erase this one. I'm going to erase this one because that is a saturated fatty acid. But this is going to count off. Our delta scheme is going to say 1, 2, 3, 4, 5, 6, 7, 8, 9. So delta 9. A double bond is between carbons numbered 9 and carbon 10. Now, delta 9, 12. That tells us, again, starting from the same location, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's one double bond. And then 10, 11, and 12. There's my second double bond. 18:3, delta 9, 12, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's 9, 12, and 15. The delta numbering scheme tells me exactly where my 2x, I'm just going to say 2x bonds, my double bonds, are. Okay, so that's the benefits of the delta numbering scheme. The alternative scheme, our omega scheme. So omega, I'm going to start out with arguably the most complicated, and that's this last one. 18:3, N-3. First and foremost, with the omega scheme, you might see N or you might see omega. -3, okay? Here's where it gets complicated. I know that with 18:3, I know that my fatty acid has 3 double bonds. What does N-3 tell me? Well, where the challenge is that it tells me where my first double bond is. So what's kind of implied with this is that when you see N minus 3 or omega minus 3, but you've also seen this 18:3, that you do follow the naturally occurring fatty acid pattern of D, S, S, D. So double, single, single, double. The challenge is that this doesn't tell me omega minus 3, comma, minus 6, minus 7. It doesn't tell me anything like that. Instead, it just sort of implies like, hey, this is a naturally occurring fatty acid, so your double bonds are going to be found in this pattern. Now, that's one challenge. The other challenge is with the omega numbering scheme, you always have to remember that the omega scheme is different from the delta scheme. The omega scheme is starting from the methyl end, so the methyl terminal. So the opposite of our organic conventions in our numbering. So this 1, that carbon number 18, which is proper for our organic numbering scheme, that's actually going to be carbon number 1, 2, and 3 for our omega numbering. So that's carbon 3 to 4. Then our next double bond, where do we find that? Well, our next double bond is going to say carbon number 3 is where our first double bond is. Carbon number 4, so it's 3 to 4. 3 to 4 has a double bond. Then 4 to 5. Well, that has a single bond because we've got DSSD. 4 to 5 is a single. 5 to 6 is also my next single. 5 to 6. And then 6 to 7 is where I'm going to see my next double bond. So 6 to 7 is a double bond. Okay, so that gets me 2 of my double bonds. Then 7 to 8, 8 to 9, and 9 to 10 is where I'll see my next double bond. So this numbering scheme is a little bit tricky because, one, you have to have that prior knowledge that your bonding pattern or your double bond pattern is not a conjugated system. Instead, it's going to be DSSD. So double, single, single, double, single, single, double, single, single, double, single, single, double. So it's helpful if you are comfortable with that. Between the two of them, why do we have both? Well, they largely arrive from different backgrounds. The delta numbering scheme, if I remember correctly, is more from the chemist perspective, whereas the omega numbering scheme is from the perspective of, or from the field of nutrition. And so, you know, whenever you talk about them or whenever you're kind of asked to draw, you have to keep a couple of things in mind. So omega, our numbering starts from the methyl end. So that's an important thing to keep in mind. All right, so we've talked about our individual fatty acids. We've talked about saturated versus unsaturated. We've talked about the naming conventions, some physical properties like our melting points and how those change based on saturated versus unsaturated fatty acids. Next up, what I'd like to talk about are basically the closest thing that you get to when it comes to fatty acids and whether or not they form a polymer, which it's important to know that fatty acids or lipids, are a major class of biological macromolecules that do not form a polymer. Now, this is what I would say is the closest to a polymer, because whenever I think of polymers and whenever I think about DNA or protein, we're talking about hundreds of these building blocks stacked up together. Triacylglycerols are 3 fatty acids connected through one glycerol backbone. So that's as close as we're going to get, and that's not a bad thing. So here's our glycerol backbone, carbons 1, 2, and 3. And then what we can form are molecules known as triacylglycerols. These triacylglycerols are going to have, well, first and foremost, we're going to have our carboxylic acid that is bound to our carbon through an oxygen. So we're going to have an ester linkage there that connects each one of the carbons of our glycerol molecule to our fatty acid, to our carboxylate ion. Now here is an example of a triacylglycerol. So the fatty acid, this triacylglycerol that's depicted here, what this is implying with this name, or what this is showing with this name, is that at carbon position number 1, we have a palmitoyl acid at carbon 1 on our glycerol molecule, linoleoyl acid and a stearoyl acid at position number 3. Now, I'm not going to, since this is bringing in questions of, or this is bringing in identifying information of like the common names for fatty acids, that's not something I'm expecting of you, but I just want to give you that context. Now, there are some IUPAC rules in terms of nomenclature priority, and that all boils down to the length of the fatty acid and saturation versus unsaturation of that fatty acid. Fatty acids, or triglycerides, or triacylglycerols, those two terms are interchangeable. So a triglycerol or a triacylglycerol is the same as a triglyceride. They are triesters of glycerol. Most contain 2 or 3 different types of fatty acid residues, and that's what we've depicted in the previous one. So I want you to be able to draw them in a couple of different forms. So here's one kind of cartoony model where we have glycerol and then fatty acids. Then this next would be a little bit more of a more accurate, showing all of the different atoms. And then here, this one at the bottom, this would be one where we're looking at, well, position number 1, position number 2, position number 3. What do we have? We have a 16:0, so a fully saturated fatty acid here, a mono unsaturated here, and then a poly here. 16:1 delta 9, 18:2. Okay, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So delta 9, comma, 10, 11, 12. 9, comma, 12. So be able to draw these based on information that I provide you with. And here's our, specific structure is generic and a cartoony structure. Okay, so animal fats typically have a high percentage of saturated fats. So one of the reasons that lots of nutritional advice is, hey, lay off the saturated fatty acids, because they're likely, or sorry, lay off of red meat or bacon, because animal fats have a high concentration of saturated fatty acids. Plant fats, by comparison, have a high percentage of unsaturated fatty acids. If we look at olive oil versus butter. Butter would be kind of a processed animal fat. With butter, you've got something that is a solid at room temperature, and you've got a high percentage of saturated fatty acids. Whereas olive oil is going to be a liquid at room temperature. And what do you have? You have a higher percentage of unsaturated fatty acids. Beef fat compared to butter, well, beef fat's going to be a little bit more of a solid at room temperature, so it's got a higher percentage of saturated fatty acids ranging between 16 and 18 carbons long. Now, the melting temperature of fatty acid varies with the degree of saturation and the length of that chain. That's kind of what we've already talked about. In this figure right here, this graph, I really like this one, and I think it's an important one to keep in mind. The more comfortable or familiar you are with that graph, the more that a figure that we're going to talk about later on when we talk about membranes and membrane integrity, the more that will make sense. Now, the biological role of triacylglycerols. They function as energy reserves in animals. If somebody has a high concentration of triacylglycerols or triglycerides, that means that they have a lot of energy that's available for them to extract. The fat content of a normal human allows them to survive starvation for 2 to 3 months. Triacylglycerols function to insulate, so in some conditions it will actually be a benefit to have more body fat. And this is something that, of course, triacylglycerols and fat content and body fat content, that brings up lots of different topics and lots of different anxieties, fears, whatever. And so this is something that people want to try to work with a little bit. And back in the mid 1990s, there was a substance known as olestra, which is a carbohydrate-based fat substitute. Now, olestra was a molecule that was developed by Procter & Gamble, P&G, which is one of the Fortune 50 companies in the world. It's a, I don't know, yeah, I think it's fair to say that it's a multinational corporation. It's one of the biggest companies in the world. They're based in Cincinnati, Ohio, and they have roots in the soap development and rendering of pig fat into soap. So that's kind of where they got their origin, and one of the ways that they developed their origin and their background and their industrial role, which I'll talk about in just a second. But one of the things that they developed, I think it was in like the late 60s, they developed this molecule that looks a little bit like this. And so it had this ring, and then it had this guy right here. And I think that one was like this. So if you're a fan of rap superstar, what's his name? Drake. He has, I think that this is like his little logo. Yeah, it's like OVO. That's a V. And I think that he recognizes it. I think his birth month is October, so it's October's very own. I think that's his thing. But it very well could be that he's just a big fan of olestra. At any rate, olestra was this molecule that had, you could put lots of fats on it. Super cool. Yeah, this is great. Lots of fat. But your body metabolizes it a little bit differently. So it doesn't go through the process of beta oxidation, breaking this down into fats, but rather it kind of doesn't know what to do with it. It looks just so crazy. And so what this allowed people to do was make Doritos, for example, or Lay's potato chips, and pack it with olestra, this carbohydrate-based fat substitute. So you could get Doritos that were low fat, but unlike other methods, they still tasted good. So it was a smiley face. And they were marketed in the mid-90s, and I believe that they were, if I remember correctly, they were Wow brand potato chips, or Wow branded, because they had this like low-fat content, but they still tasted good. And so olestra was used. And this is all good and well and everything, and for a while, I feel like I remember it was like the summer of 1995, 96, where it was like, Wow chips, no fat, awesome. I eat Wow chips all the time, that's great. But then people started to say like, whenever I ate these Wow brand chips, my stomach just hurt. And, I would have these like intense, very intense and unpleasant, I'll just say bathroom experiences. And it was largely rooted at the source, or the source of it was this olestra. It was never deemed to be like fatal or anything like that, but people were not having a good experience. And so they weren't like, got to get me some more olestra chips. And so it's like the mid 90s that slowly but surely their popularity waned, and they were ultimately taken off the shelves because nobody wanted it. But that was a source of like, hey, let's make something that people like, but they don't dislike from an energy standpoint. They like the flavor, but they don't dislike it. They're not going to say like, well, I just can't eat very much of that. At any rate, olestra, that's a carbohydrate-based fat substitute. I do want you to know that, and one valuable thing about this is, and I'm sorry I forgot this, we have a little bit of familiarity with this structure. So if you look at this, if we look at this structure right here, there we go, that right there. What kind of bond is this? This is a glycosidic linkage. So it was a glycosidic linkage that was at the heart of this carbohydrate-based fat substitute. Okay, now back to my commentary on Procter & Gamble. I bring this up because I have a very good friend of mine who works at Procter & Gamble, and I've been up there a couple of times. Procter & Gamble's based in Cincinnati, And I believe, I could be wrong, but Procter and Gamble's kind of like a, if you live in that region of Ohio, you either, and you've lived there for multiple generations or something like that, or your family has been there for a handful of generations, it's very likely that your family has been employed by Procter and Gamble for a very long time. And I bring that up because one of the processes that I don't think that they developed it or anything like that, but they definitely industrialized it, was this process known as saponification. Saponification is an industrial process by taking triacylglycerols or triglycerides and converting them into sodium salts or fatty acids. So you'd be able to release glycerol and you'd be able to make these sodium salts or fatty acids. This is also a key plot element in the movie and the book Fight Club, where they took fats and they did what's known as rendered them, those fats, so that they could make soap. So it's the process of making soap, which I've always thought saponification, it looks like somebody just misspelled soapification. Saponification is the process where you take triacylglycerols and you make these sodium salts of fatty acids. Now this is the industrial process compared to the enzymatic process. Like whenever your body ingests something that has like animal fat that has triacylglycerols, your body is going to use a class of enzymes known as lipases. Lipases in water, and you're going to undergo this hydrolysis reaction where you release tons of these ionized fatty acids. So these are ions, but they just don't have the sodium associated with them. Now lipids are ultimately classified in two major groups. Just like most everything, you can classify it as being polar or nonpolar. Now when we look at a triacylglycerol, this is a molecule that is a nonpolar molecule. We've got this glycerol backbone, and then our R groups here are fatty acyls. These are alkyl chains. Those are a bunch of hydrocarbons. Now they do have this ester linkage, but ultimately that's a nonpolar group. Yeah, sure, this right here is somewhat polar, but it's nonpolar and nonpolar on opposite sides of one another. They more or less cancel each other out. Now in the case of a glycerol phospholipid, well, what you have there is you have a phosphate group, and then you have an X that's going to have some modification to it. Last is our sphingomyelin. Sphingomyelin has that same sort of glycerol backbone, but then we've got linkages to fatty acids. Now, you're not necessarily going to have an ester linkage, but one thing that you're going to definitely have is something like this. This is akin to what you see in a glycerophospholipid. Now, with all of that said, your nonpolar lipids, like your triacylglycerols, they're primarily going to serve the purpose of being energy storers. And then your polar lipids, these and these, respectively, are the basis of lipid bilayers. So when you visualize a lipid bilayer, something like this and this group right here is that right there. This group right here could also be that right there. That's where your polar head group is coming from. These chains right here, just let me erase some things so that it's a little bit less jumbled. Erase all this, erase all this, erase That is going to make up this right here. Okay. Now, glycerophospholipids, they're an important molecule that you should be familiar with. These are the major lipid component of biological membranes. Amphiphilic molecule. They are amphiphilic molecules. That means our definition for amphiphilic is that something that has a nonpolar and a polar region. So these are amphiphilic molecules with nonpolar aliphatic tails here and here, and a polar phosphoryl head group. So if you look at this model for our glycerophospholipid, we've got a phosphate group right here, and then this X that's kind of obscured there. That's where you're going to have some modification. That's where you're going to have something that makes it a little bit different. We've got an example over here where I have an X remaining, or a star remaining. This is an example of a glycerophospholipid. This right here is a molecule known as choline. This is a molecule of phosphatidylcholine, sometimes represented as PC. This is an important part of biological membranes. Now, this head group here has a positive charge. It is polar, whereas these hydrocarbon chains right here, they are nonpolar. I want you to be able to draw them, and I want you to be able to draw a molecule. If I provide you with what the head group, this X right here, is, I want you to be able to draw that. Now, the questions that you should anticipate would be something like this. You know, draw a glycerophospholipid with C1 that has a C18:2 omega minus 3. And then at C2, draw C16:1 delta 11. So this is kind of tying all the things back together. And then at C3, you want to draw the phosphate. Then what you also want to draw is whatever that head group is. Serine, I provide that as an example. Now, there's a total of 5 head groups that I want you to be familiar with. We'll see those right here. These first 5 right here. I want you to be able to draw those groups. So those are going to, oh, that's glycerol, I don't need that one. Those are going to take the place of this X right here. In the example of water, it's just a hydrogen. In the example of ethanolamine, we've got something that's a little bit more to it. We've got this right here, CH2, and then NHH plus, okay? So when you see these formulas, make sure that you can translate it from this single line to a model that looks a little bit more like this, where you have a little bit more depth. You can look at it on the X and the Y plane. Now, all of these molecules, all these glycerophospholipids, they're different. So when you think about a lipid bilayer, you've got phosphatidic acid, you've got phosphatidylethanolamine, phosphatidylcholine, phosphatidylserine, phosphatidylinositol. All of these are major components of membranes, and they serve different purposes. They're going to play different roles in terms of signaling, whether it's a molecule perceiving a signal or displaying or projecting out a signal. The composition or the abundance of these different phospholipids is going to have an impact on basically what a cell's communicating. So if you take something like phosphatidic acid, if there's a high concentration of phosphatidic acid displayed on the exterior surface of a cell, that means that cell's under stress. Now, the importance or the role that each one of these different glycerophospholipids play and what they communicate, that's not something I'm expecting in this class. But I want you to know basically what a glycerophospholipid does. It communicates. It says something about the health or the well-being or the ongoings inside the cell. So with that, I do want you to be able to draw these 5 different structures. Now, what's important about them is that basically they are connected. They are taking the place of this X right here. So if we look at myoinositol, for instance, what that looks like is this right here. A 6-membered ring with a bunch of hydroxides. Now that's significant because when you think about a hydroxide, one thing that can be done to a hydroxide is it can be used to add something. For instance, you could add a phosphate group. When you add a phosphate group, that's going to change the types of interactions that this molecule has. So at any rate, I want you to know these first 5 and be able to draw those first 5. I want you to be able to draw them in this kind of cartoony fashion, in a generic fashion, and if I give you specific information. All right, well, I hope that was helpful, and I hope that you have a good one.